So in this hour, we are going to see the physical chemistry too. Actually, at present, we are discussing the biophysical chemistry, and I will share the PowerPoint. So the last class, we did the 3 calculations. And in the 3 calculations, so we have taken the weak acid and its a weak salt. For the first study, we have taken them with the equal volume and equal concentration. And we have seen what happens to the pH of the buffer after the addition of 1 ml of 0.1 molar hydrochloric acid, and the change of the pH is 0.09. And then in order to make a small difference, we diluted both the salt and the acid, but we have taken equimolar and equal volume. Then the change in pH was a little high. And in the third case, we have taken unequal volume mixture or unequal concentrations. That means in our study, we kept the concentration constant, but we changed the volume. But as a whole, there is a concentration change. That is how we should understand. So then also the difference, the change in the pH was comparatively high. Therefore, comparing the 3 things, we have come to a conclusion. A good buffering is achieved when the acid and the salt of high concentrations were taken, and also when their concentration ratio is unity, there is a little change of pH. And then the normal range depends upon normal range of a pH is 2 pH units, that is either side of the pKa value of the buffer. And therefore, we have listed a number of buffers. Lactic acid sodium lactate buffer will have the buffering capacity between 2.86 and 4.86, and the phthalic acid and the potassium phthalate buffer from 3 to 4, and acetic acid and sodium acetate buffer 4 to 6, and the monosodium dihydrogen phosphoric acid and disodium salt or phosphoric acid, they show the buffering range 6 to 8, and according to buffering range, buffers are chosen. Now, in a biological system, how we are going to choose the buffers for the biological systems, that is very important, because that involves a lot of control measures. Lot of control measures we have to take into consideration. Just a minute, I want to share slides. Okay, now look, so these are some precautionary informations about commonly used buffers. When you choose a buffer for biochemical reactions. You should take that buffer with the correct pH range, and the buffer should not inhibit enzymes. See, biological systems have plenty of enzymes, and these enzymes should not be inhibited by the buffer which we are going to use. And also the buffer should not precipitate polyvalent cations. And also the buffer should not be toxic. And also the buffer should not absorb ultraviolet radiation. And also it should not change its pH with the concentration and the temperature. When the temperature changes or when the concentration changes, the pH of the buffer should be remaining constant. It should not vary abruptly with concentration and the temperature. So these are all the some of the important characteristics expected of a good buffer, which can be used for biochemical studies. So we are going to see some of the commonly used buffers and what are all the precautionary pieces of information to be known about these buffers. The first buffer taken into consideration is a phosphate buffer. This phosphate buffer is of very high buffer capacity. I've already told you what is a buffer. Buffer is a chemical system which can maintain its pH for small additions of an alkali, a base, or an acid. The phosphate buffer has a very high buffer capacity, but the sodium or potassium salts of the phosphate buffer, they are highly soluble, and because of their higher solubility, the mu, the ionic strength of the buffer solution is very high, because the sodium potassium salts, they dissolve to a greater extent. Therefore the ionic strength of the solution will be very high. Now I want to prepare a buffer with a high buffer capacity at the same time with a low ionic strength, which is not possible in the case of a phosphate buffer to prepare a buffer with a high buffering capacity and with low ionic strength. So that is one of the disadvantages of a phosphate buffer. And also phosphate buffers, they can very easily bind with the calcium 2 plus and the magnesium 2 plus ions. And also
Sir,
phosphate, yes, pa.
sir, 20 UCH போட்டு வந்திருக்காங்க சார் உள்ளங்க. யாருன்னு தெரியல.
Just a minute, I'll see. So this phosphate buffer is toxic to mammalian cells. Mammalian means animals can be divided into two kingdoms: vertebrates, invertebrates. Vertebrates are the animals with a spinal cord. Invertebrates are the animals without a spinal cord: protozoa, porifera, coelenterata, platyhelminthes, ascalminthus, annelids, arthropods, molluscs, echinodermates. These 9 classes are there in the invertebrates. Vertebrates: aphids, amphibians, reptiles, and mammals. So the last one is the mammals, but we are all mammals. Human beings are mammals. These phosphate buffers are toxic to mammalian cells. And also the phosphate buffer can work better in the range 12 to 12.5 pH. But the buffering cannot be achieved between 7.5 and 8. So these are the characteristics of a phosphate buffer. So while choosing phosphate buffer for biochemical applications, these things are to be had in our mind. Their salts are highly soluble, therefore their ionic strength is very high. Therefore, it is not possible to prepare a phosphate buffer with a high buffering capacity and a low ionic strength, and they are able to easily bind with calcium 2 plus and magnesium 2 plus ions, and also they are toxic to mammalian cells, and they lack buffering in the range 7.5 to 8, and they are acting as good buffers in the range 12 to 12.5. See why the binding with the polyvalent cations is to be considered very serious. Our biological system contains plenty of polyvalent cations like a calcium 2 plus, magnesium 2 plus, iron 2 plus. These are all some of the important cations present in our
Sir,
biological system.
sir.
Yes, pa?
திரும்பி அந்த நம்பர் உள்ள வந்துட்டேன்.
Wait just a minute. So phosphate buffer. So these are all the things to be taken in your mind before going for a buffer for biological studies. Now look here. Next buffer is a carbonate buffer. Most of the carbonate of metal ions are insoluble, and also they are very much sensitive to temperature. At high temperature, the pH change will be very high. That is, extreme pH change is observed at high temperatures. It is because of the elimination of carbon dioxide from the system. But carbonate buffers can work between 10 to 10.8. So these are all the important points about carbonate buffer. The next one is a tris buffer, which is also very often used in the biochemical studies. The advantages of a tris buffer, the pKa value is 8. Therefore, it can buffer between 7.5 and 8.5 pH. It is of very low toxicity. The toxicity of a tris buffer is very low, and also it does not show any interference with the biochemical reaction. And also it is very much available in pure form. It is available in pure form. So these are all the advantages of tris buffer. Disadvantages of a tris buffer. Temperature dependence. With the temperature, it changes its pH. Temperature dependence. And it reacts with the copper 2 plus, calcium 2 plus, nickel 2 plus, and silver plus ions. And react even with the glass electrode. Why suddenly glass electrode is introduced means, suppose if you want to find out the pH of a buffer solution, the very easy method is to have the combined pH meter. Combined pH meter is nothing but the glass electrode coupled with the silver chloride electrode. Even the glass electrode is made of a special type of a glass which will act as a membrane. This tris buffer is able to react even with the glass electrode. Therefore, even the determination of pH experimentally using the glass electrode is not possible, because tris buffer will easily react with glass electrode. And next one is EDTA buffer. EDTA buffer, it shows So that is about the Trish buffer. Next one is EDTA buffer. EDTA buffer is a good chelating agent for divalent cations. You know what is a chelating agent? You might have studied in the inorganic chemistry. And this EDTA buffer is normally added to reduce the concentration of divalent cations because it will chelate and it will take off. Therefore, if you want to reduce the concentration of divalent cations in a system, you can add EDTA buffer that will reduce the concentration. And this is very much needed while you are working with the nucleic acids, because Mg2 plus ion is also a divalent cation, which is a cofactor for many enzymes, which can be chelated using the EDTA buffer. Therefore, while you are working with the nucleic acids, this EDTA buffer is preferable. And one of the disadvantages of this one is it will absorb UV radiation, ultraviolet radiation it will absorb, and also its working concentration should be of the order of 0.001 molar. Higher than that, it's not advisable to work with. So its concentration should be around 0.001 molar. So these are all the important characteristics of EDTA buffer. The next buffer is boric acid and glycine buffer. See, boric acid and glycine buffer, they are very weak toxicity. They are of a very weak toxicity. And they show UV absorption. And boric acid can function as a buffer between the pH 8.7 and 9.7. And glycine can work between 9.5 and 10.3. Glycine can work between 9.5 and 10.3. And the borate buffers can be used while we are working with the bacteriophages. So these are all the important points about boric acid and glycine buffer. So the next one, glycine buffer. Glycine buffer, you know, from the name itself, you can understand that it is a protein-like substance. Two amino acids are coupled together. It is a peptide. You know what is a peptide linkage? Amino acids contain both amino group and acid group. Therefore, when two amino acid molecules come closer, the amino group is basic, acid group is acidic. Therefore, they can react between them. Therefore, what will happen? After the elimination of one molecule of water, amide bond is formed, which is called a peptide linkage. Therefore, this glycine buffer is a peptide. The linkage is called a peptide linkage. This peptide linkage can be easily cleaved by enzymes and also even by simple hydrolysis. They can be cleaved. So that is why even some poisons, proteinous poisons, or you can take the insulin. Insulin is not administered orally as a tablet because insulin is a complicated protein with many amino acids. So when you swallow the tablet, once the tablet goes into the stomach, in the presence of strong acids, the insulin protein will break and it will be broken into amino acids. So insulin is totally inactive in the form of amino acids. It is active as long as it is a complex protein. That is why always insulin is injected. It is not given in the form of a tablet. Because in acid environment, the peptides will get cleaved. Similarly, this glycine buffer is a peptide. It can be easily cleaved by the enzyme protease. Therefore, glycine buffer cannot be used because of its ability to cleave, because it can be cleaved easily in the presence of enzymes. But it can be used in the enzymological works. And the buffering range is between 7.5 and 8.0. And it shows very low UV absorption. Enzyme active assays in the UV range will not be impeded, and it has no affinity for divalent ions such as calcium 2 plus or magnesium 2 plus. Therefore, it has no affinity for divalent ions. So these are all the important characteristics of a glycyl glycine buffer. So the next buffer is triethanolamine buffer. This is also used for enzymological work, and it has advantages of a glycyl glycine buffer. So what are all the advantages we have seen in the glycyl glycine buffer? This triethanolamine buffer, it has the advantages of a glycyl glycine buffer, but it does not have the limitations of glycyl glycine buffer. So that is the speciality of triethanolamine buffer. So next one, good buffer. So it is not a good or bad buffer. It is the buffer synthesized by a scientist called Norman Good. That is why it is called a good buffer. It is a Zwitter ionic buffer. What is a Zwitter ion? Zwitter ion means the amino acid unit, the amino group can become an ion by gaining one proton, NH3 plus. On the other side, COOH can become COO minus by losing one electron. So one electron from the acid side, when it comes to the amino group side, the amino acid molecule will have both polarity. One side it is positively charged, on the other side it is negatively charged. Such ions are called Zwitter ions. Zwitter ions. So these Zwitter ions, suppose if you subject a Zwitter ion into an electric field, if a cation moves towards the anode and the anion moves towards the cathode, this Zwitter ion, one single ion having both the charges, will not move anywhere. So what is the pH at which this Zwitter ion formation is there is called isoelectric point. So these are all the things you might have already known. So this good buffer is a Zwitter ionic buffer, and it is non-toxic, and it does not absorb ultraviolet radiation, and this buffer, it does not precipitate divalent cation, and it also does not have temperature sensitivity. When temperature changes, it retains its form and functionality. So they are all the characteristics of a good buffer. So we have seen various buffers and their precautionary informations, and what are buffers and how buffers are working. And we have seen this Anderson-Hasselbalch equation to calculate the pH of a buffer, and these are all the things we have seen.